So hi everyone, this is your mentor educator Akash Sagi, finally back with a very important lecture. And in this lecture guys, this is going to be a very one short lecture, and this is going to be a very short lecture on some basic principles, some basic principles of purification and quantitative analysis and qualitative analysis of organic compounds. And guys, we're gonna start this one shot just now. All right then. So first of all guys, let me tell you one thing. What we gonna do in this lecture. Let's look at this. First of all, we are going to cover purification, qualitative and quantitative analysis of organic compounds, guys. All right then. Okay, in this session guys, we are going to cover, all right, okay, purification. We are going to cover qualitative analysis, quantitative analysis. All right then, this is going to be a very short lecture. Let's start with our first topic, which is the purification of organic compounds, guys. First of all, let me tell you one thing. When we try to purify organic compounds, we have a lot of methods to do so. All right, some of the methods can be used in some, when the organic compound have some different properties. Okay, for some different compounds, when they have some different properties, we have to use some other method. All right, so in total we have 8 total different methods of purification of organic compounds. We will start from filtration. Okay, what is filtration? What is the principle of filtration? When we have to use filtration for that particular organic compound, what should be the properties of that organic compound so that we can use filtration? So a lot of things we have to discuss in this topic, guys. All right then, we'll discuss then sublimation, distillation, fractional distillation. All right, distillation under reduced pressure, very important, steam distillation, differential extraction, and then chromatography. And after doing all these purification methods, then we'll move to our qualitative and quantitative methods, or the topic. All right then guys, let's start the session with the first topic, which is filtration. Okay, so filtration is one of the very important method in which we are trying, we will try to purify our organic substance or organic compound. But let's understand when we will use filtration. All right then, the process of filtration is used to separate an insoluble solid component of the mixture from the soluble component of a given solvent. Now let's look at this. Let me tell you what, when we have to use the method filtration. Let's suppose you have a beaker in which you have your organic compound along with impurity, guys. All right, organic compound plus impurity. Now what you will do in this method, guys, you will add a solvent into it. And the case will be that either organic compound or either impurities are going to dissolve in this solvent. Only one of them, either organic compound or either impurities. Now let's suppose if impurities are completely soluble in this solvent, then you will have a solution of impurity plus solvent, but your organic compound is remain in solid downside of the beaker, and then you will use filtration. How will you use filtration? Now let's look at this diagram, guys. You have this beaker, all right, then you have this funnel, and you will have a filter, filter paper on this side. If you look at this, this is the filter paper, guys. This is the filter paper. And now after dissolving this solvent into this organic compound plus impurities, in which the solvent is completely soluble in impurities but not organic compound, then you will filtrate this. Just because organic compounds are insoluble, they are in solid state, they will be filtrated out from this funnel, and then you will have the final filtrate, which is nothing but solvent plus impurities, and on the filter paper you will have your organic compound in its pure form. So this is when we use filtration. So in filtration, you have to make sure that one of the part, either impurities or organic compound is completely soluble in the solvent and other one is not. For example, naphthalene and urea, guys. Naphthalene and urea can be separate out by this technique. Why? Because we know very well that urea when added into water is soluble, okay, but the naphthalene is not soluble in water. And just because we'll have the filtrate of urea plus water in the beaker, in the final beaker, and we'll have the naphthalene particles on the filter paper, guys. So this was the first method, for the purification of organic compound. Let's move to the next one, guys. All right then, the second method is sublimation, guys. Now what is sublimation? First of all, let's understand what do we mean by sublimation. All right, if any substance can directly converted into its gaseous state, this is what we call as the sublimation of that particular substance, guys. All right, okay, this is what we call as sublimation. If anything can directly convert from its solid state to the gaseous state, this is what we call as sublimation. Now let's understand what is sublimation and how we can use this to purify an organic substance. What is the principle behind it? All right, look at this. Now the sublimation process is used for the separation of a sublimable volatile compound, okay, from a non-sublimable impurity. Is very, very simple. Now look at this. Let's suppose you have a solution, of your organic compound plus impurities. All right, now out of these two, guys, one is sublimable. Okay, sublimable, it means it can directly convert it into its gaseous state. Okay, but now the impurities are non-sublimable, guys. They are non-sublimable. Okay, they are non-sublimable. It means they will not convert, they will not convert themselves from the solid into the gaseous state. It means they will remain in the solution and your organic compound is going to be in the gaseous phase, which you will collect. Let's look at this diagram. In this diagram, you again have this, you have this china dish and you have this burner. Okay, you are giving the water bath to this beaker in which you have the impure compound, guys. Let's look at this. This is the impure compound. Now, when you heat it, with a very small amount of heat, one of the part, either the organic compound or the impurities, whichever is sublimable, is going to produce the vapor, and it will just pass out the filter paper, okay, which is right there on the surface. All right, guys, but the other thing, which is the impurity, okay, which is non-sublimable, will remain as it is here. So it means we will have the organic compound in the vaporized form here, which we can collect after this, and we will have the impurities as it is in the solution. And this is how we can use sublimation. We can use the sublimation to purify our organic compound. Now in this process, the impure solid is taken in a porcelain dish and covered with a perforated filter paper. Guys, look, you can look at this. This is the filter paper from which the vapor can pass through, but not the impurities. Why? Because impurities are completely present in solid state, so they cannot pass the filter paper. They are non-sublimable. For example, let me give you the example. One very important thing, guys. Okay, so example of all these methods are very important. Question will ask you 99% time, okay, from this topic, they will ask you the examples. Okay, so which substance, which organic compound can be purified by this method or by that method. So this is very important for you to remember the examples along with the principle. All right, so principle is one of the thing, either organic compound or impurity should be sublimable, other should be non-sublimable, the first thing. And the second thing is example. For example, if we want to purify camphor, if we want to purify naphthalene, if we want to purify anthracene, if we want to purify benzoic acid, in all these cases we have to use, guys, sublimation, the technique to purify these organic substances. All right, so this was sublimation. Let's move to the next one. One of the most important one and one of the most interesting method to purify your organic substance, guys. One of the very useful one. All right, let's understand distillation, guys. Let's understand distillation. What do we mean by distillation? The method is used for the purification of liquids, first of all, which boil without decomposition. So what does it mean? Okay, I'll tell you. And contain non-volatile impurity. Now let's understand this. Let's suppose you have an organic compound CX, HY and OZ. All right. You need a temperature to boil it. This is what we call as the boiling point. All right, guys, it will just convert, from this liquid to the gaseous state at this temperature. But there is a minimum temperature at which the substance decomposed. Okay, temperature at which it get decomposed, it means it is not going to be vaporized, but it will decompose into 2 or more substances. All right, guys, so distillation can be used for those organic compounds which will not decompose first, either they will convert themselves into the gaseous state at their boiling point, guys. All right then. Okay, so the method is used for the purification of liquids which boil without decomposition and contain non-volatile impurities. Very, very important. You can say non-volatile or less volatile. What does it mean? Let's try to understand this. Guys, let's suppose you have A substance plus B. Let's say this is the organic compound and this is the impurity. Alright guys, this is the organic compound, this is the impurity. Both may have a certain boiling point, guys. Let's say the boiling point of A is TABP, okay, and boiling point B is TBBP. The boiling point of B, the boiling point of A. Guys, let's suppose if the boiling point of these two, either impurities or the organic compound, is very, very different. Alright, is very, very different. Let's suppose the boiling point of this A is, for example, let's say 50 degrees Celsius, and the boiling point of this A is 150 degree Celsius. So what you will do? You will take this impure solution along with the organic compound in this, beaker type, and in the porcelain dish, and you will give it the water bath, and you will, turn on this burner, and just because of the heat, the temperature will start to rise of this whole impure solution. When the temperature will start to rise from 0 degrees Celsius or from, let's say, 10 degrees Celsius, it will going to rise up to 50 degrees Celsius first. All right. As soon as it is getting close to 50 degrees Celsius, your A is going to be, guys, vaporize. Your A is going to be vaporized because this is the boiling point of A. And as soon as the A is going to vaporize, but B is as it is in the solution because the boiling point of B is 150 degrees Celsius. All right. So it will only starts to boil when it is very close to 150 degrees Celsius. And, right now the temperature is only 50 degrees Celsius. So what will happen then? So from at 50 degrees Celsius up to 60 or 70, only the A will be there in the vapor phase, which you will collect from here and you will pass it into the Liebig's condenser, and this condenser will help us to convert this vapors of A again into its liquid state, and will have the pure A. Now let's suppose this, okay, we already suppose this to be organic compound. So, we have, by this process, will have after some time the pure vapor of A, which is then condensed back into the liquid state, and until it reaches to 150 degrees Celsius, we will have the pure amount, the pure liquid of A. This is how you use the technique distillation to purify your organic compounds. Let's look at this. In the simple distillation involves the heating of the liquid to its boiling point so that it is converted into vapors. On cooling the vapor, pure liquid is obtained and collected separately. We collected the pure organic compound separately, all right, and the impurities is there just because, it will take 150 degrees Celsius for it to get vaporized, guys. For example, okay, which of the organic compound, along with the impurities can be separated out with this method? All right, guys. So, other than impurities, we can also separate two different organic compounds using this technique if they have very high difference in their boiling point. For example, chloroform and aniline. If you look at this, aniline will boil at 457 Kelvin, and chloroform will boil at 334 Kelvin. All right, there is a huge difference. So you will start to heat your whole solution in which the aniline and chloroform is present. As soon as the temperature reaches 334 or 340 Kelvin, your chloroform will vaporize. You will collect it by passing it into the Liebig's condenser, and then you will have its separate form in the other beaker, and you'll have the aniline in the separate beaker. This is how you can purify all these things, either ether and toluene, because they have a lot of temperature boiling point difference. You can you can separate out benzene and aniline. All right then. Okay, so this was your distillation. Okay, now let's move to the fractional distillation. Now look at this, what we were using, the simple distillation method. This was the simple distillation method, by the way. This was the simple distillation method. Simple distillation method only works if the difference in the boiling point of the two things, either organic compound with impurity or the two organic compounds which you want to get separated. All right, guys, if the difference between those two things are very, very, very high, let's suppose the difference should be more than 25 degrees Celsius. Okay, the difference in boiling point should be more than 25 degrees Celsius. Only then you can use simple distillation. If the difference is less than 25 degrees Celsius. Now it is very hard to separate these two things. Why? Because in the with the very small difference in the boiling point, both the organic compounds will start to vaporize one by one, and then it is very hard for you to get them separated, just because both of the organic compounds converted into the vapor state, and then you cannot separate them. You understand this? All right. So simple distillation has a limitation that if the two organic compounds or the impurity and the organic compound have boiling point difference less than 25 degrees Celsius, then you cannot use the simple distillation. You have to use the next method, which is the further the advanced technique of distillation, which we call as fractional distillation. So first of all, fractional distillation is used when the difference in the boiling point of impurity in the organic compound or between the two organic compounds, guys, is less than 25 degrees Celsius. Yes or no, my boys and girls? All right, very clear? All right then. Okay, so difference should be less than 25 degrees Celsius, the first thing. Now, so what we will do if the difference is very, very less and both of them will start to vaporize one by one, so it is going to be very hard for us to separate them. Now, what will we do? All right. In this technique, we will add one more thing in our experimental, in our apparatus arrangement, and the one thing is going to be fractioning column, guys. Fractioning column. Fractioning column. Now, what do we mean by this fractioning column? Now, let's look at this. All right. The process is used to separate mixture of two or more miscible liquids. They are miscible, okay, which have boiling point close to each other. What is the meaning of boiling point to be close to each other? It means it is lesser than 25 degrees Celsius. The difference between the boiling point is lesser than 25 degrees Celsius. Then we will use fractional distillation. Guys, in these cases, the process of simple distillation will fail because the vapor of both the liquids will be formed simultaneously. One by one, simultaneously. This is the problem. All right. To solve this problem, the distillation is carried out by using fractioning, or we can say fractioning column. Now, what is this? Now, let's look at this. We just add one more thing in our apparatus setup, and this is nothing but this is the fractioning column, guys. This is what we call as fractioning column. Now, let me tell you this in a very simple way. How will you understand the use of fractioning column? First of all, let's understand the purpose of fractioning column, and to understand the function of fractioning column, let me give you one example. Let's suppose you have two organic compounds which you want to separate, A and B. All right. Let's say the boiling point of A to be 50 degrees Celsius and the boiling point of B to be, let's say, 65 degrees Celsius. All right. You have heated both of them. You have heated, both of them together because they are a mixture immiscible. They are the two miscible liquids. All right, 65 degrees Celsius. And now you start heat the miscible mixture of these two. All right. Now let's look at this. Fractional, fractioning column is nothing but a column like this. All right. You will have a tube having obstacles from bottom to top. Let's look at this. Okay, let's understand with this fractioning column. If you look at this fractioning column, or let me give you one more example or one more diagram of this fractioning column. Okay, this fractioning column is nothing but after vaporizing your miscible mixture, you have to pass your miscible mixture from this fractioning column, and this fractioning column is going to help you to separate out the both organic compounds having very similar boiling point. Now let's look at what is fractioning column. So what will happen in this fractioning column? You will add some obstacles in the path of the vapor phase of the miscible liquid. Now what will happen? So you are giving a temperature. You are giving a temperature from here. Okay. Now let's suppose you gave a temperature, let's say for example you gave 65 degrees Celsius, because the difference is not is very very less. So it is not in your hand that you will have this temperature to be very precise 50 degrees Celsius. Now let's suppose you give the temperature to be 65 degrees Celsius. Just because of this, both A and B starts to vaporize, both A and B starts to vaporize. But before this, in simple distillation, we didn't have any fractioning column. So if we use that process, both of them will travel from here to there and will get vaporized and will go into the condenser, Liebig's condenser, and they both will get condensed together, and then again they will be a miscible, a two miscible mixture. All right, guys. But using this fractioning column, what will happen? This fractioning column is, giving some obstacles in the pathway. Just because of that, the movement of vapor becomes very, very, very lengthy process. And during this lengthy process, let's suppose the vapor of A is traveling from here, from here, from here. And the temperature at this point was 65 degrees Celsius, just because they both of them vaporized. But when they have to go through with a lengthy process, having some obstacles, so the temperature of these vapors will start to decrease again, just because you have the place which is 60, the temperature at which the 65 is 65 degrees Celsius. But as soon as you are going away from this heat, the temperature will starts to decrease. Now just because of this, when the temperature decreases, all right, both for A and B the temperature decreases. So let's suppose till here the temperature of A and B both decreases from 65 degrees Celsius to 55 degrees Celsius, just because of the traveling, okay, and they are very far away from the the heating point right now. But now at 50 degrees, at 55 degrees Celsius, the B will not be in vapor state. It will again get condensed, and it will just stick down to these obstacles and condensed back, just because the temperature decreases, okay. So this will get condensed back into the liquid form and will come back to the beaker. And the other one, the A, whose boiling point was 50 degrees Celsius, even after decreasing the temperature, it is 55 degrees Celsius. So it will remain in the vapor state and it will pass into the Liebig's condenser. And this is how, by using this fractioning column, which is nothing but creating a lot of obstacles during in the path of the vapor, and that's because of these obstacles the temperature decreases. One of the organic compound remains in vapor state and will go into the Liebig's condenser and get separated, but other one get condensed back into the liquid state into the beaker. This is how we use fractional distillation. The example of where we use the fractional distillation is acetone and guys methyl alcohol, just because you can see the temperature difference is very large, almost just 8 degrees Celsius, just 8 degrees Celsius. So this is how we use fractioning column here, and this is how we use, guys, the fractional distillation. I hope you are getting it very clearly. All right, okay, if not, then please let me know in the comment section. All right, then now distillation under reduced pressure, guys. What do we mean by distillation under reduced pressure? As soon as I started the whole topic of this purification, okay, and primarily distillation, I was I told you that there are two temperature. One is boiling point and one is, guys, temperature at which the compound decomposed. Now for some of the substances, the boiling point, let's suppose the boiling point is 100 degrees Celsius, for example, okay, but the temperature at which they decomposed is 80 degrees Celsius. Because of the reason, as soon as you are trying to get vaporize them, just to liquefy, just to purify them with the help of distillation, instead of getting vaporized, they will start to decompose, and you will have a complete different substance after after the organic compound getting decomposed. Now this is a problem, because you just want to purify it. You don't want to make a new substance out of this whole process. You want to just purify it. Now this is a problem, that it will first decompose, rather than it is getting vaporized, and you will have it separated into the other beaker. Now what should we do? All right, in such type of situations, we use distillation under reduced pressure. What does it mean? What does it mean of this reduced pressure? Now let's understand this. So certain liquids have tendency to decompose at a temperature below to their boiling points. Obviously, that was the case. Such liquids cannot be purified by ordinary distillation. You cannot use ordinary distillation in such type of techniques, because rather than getting vaporized, it will decompose to make a new chemical substance. Now this is the problem. Then, therefore, vacuum distillation is used. We also call this whole method to be vacuum distillation for liquid which decompose at temperature below their normal boiling point. Now this is very, very, very important to understand. You will do the whole distillation process in under a vacuum state, so that you can manipulate the pressure of that organic compound. Now let's look at this. Let's suppose you are doing this whole distillation process. Okay, here if I'm saying the vacuum, it means I can manipulate, okay, the spelling distillation, okay, the we can manipulate the pressure of that organic compound. Now let's look at this. I know the boiling point is 100 degrees Celsius. I know the decomposition temperature is 80 degrees Celsius. What if before the distillation process, I just have my whole substance, my whole apparatus of distillation into this vacuum, and I can manipulate the pressure around it. And if I decrease the pressure of my organic compound, just because by decreasing the pressure, I can say now it is more easy to vaporize it, guys. If I decrease the pressure of this organic compound, it is more easy to vaporize it. Yes or no? If I decrease the pressure of that organic compound, now again particles are very far away from each other. It means they requires very less temperature now as compared to the previous boiling point to vaporize themselves. Yes or no? If yes, then I can say that by reducing the pressure, now the temperature required to boil that organic compound decreases. Let's suppose I reduce the pressure by what factor? By a certain factor, so that the boiling point from 100 degrees Celsius comes to 75 degrees Celsius. Yes, this can be the possibility. You just have to reduce the pressure now. Yes, I can do this. Okay, if you decrease the pressure, the boiling point decreases up to 75 degrees Celsius. Now the temperature at which it is getting decomposed is 80 degrees Celsius. Or if you are saying that, sir, the temperature is very, very less at this certain point of time, maybe by mistake the temperature reaches to 80 degrees Celsius, our whole distillation will get destroyed just because the organic substance is going to be decomposed. Yes, you can again reduce the pressure more, and certainly the boiling point temperature even can reduce up to 55 degrees Celsius. Yes or no, guys? Yes or no, my boys and girls? If yes, then now boiling point is 55 degrees Celsius, the decomposition temperature is 80 degrees Celsius. Problem solved. Okay, it will get boiled first, it will get vaporized first at 55 degrees Celsius rather than decomposition, and this is how the vacuum distillation works, or the distillation under reduced pressure works. Now let's look at this. Under reduced pressure, the liquid boil at a low temperature and the temperature of decomposition will not be reached. For example, we have some examples. Glycerol boils with a decomposition at 563 Kelvin, but the pressure is reduced to 12 mm. All right, it boils now 453 Kelvin without decomposition. Are you getting it? Everything very good now, guys. Distillation under reduced pressure. Now move to the next one. Steam distillation, guys. Steam distillation. What do we mean by steam distillation? No big major change in this process. The process of the steam distillation is used for the separation and purification of liquid which is appreciably volatile but only in steam. Are you getting my point? Okay, either the impurity or the organic compound is only volatile, it will only vaporized in steam from a non-volatile component of a mixture. All right, thus the process of steam distillation is used to purify the substance which are volatile in steam. Okay, so they need steam. If you want them to be vaporized, volatile, but are not miscible with water. Okay, they shouldn't be miscible with water. They should be volatile in steam. Possess sufficiently high vapor pressure. High vapor pressure should be there just because you can vaporize that particular thing easily in the steam, and you have the, let's suppose you have the impurities which are non-volatile, so they will remain in the solution or in the beaker, and your organic compound will get vaporized, which you will collect in the next beaker. All right. Okay, so they should have high vapor pressure at the boiling point temperature of water, contain non-volatile impurities. Obviously, impurities should be non-volatile now. The only difference with the simple distillation in this case is that you have two things: one impurity which is non-volatile, and one is your organic compound which is volatile but in steam. All right. Okay, then next, move to the next one. Very important is your fractional distillation is very important in this whole thing. All right, fractional distillation is important. Now we are going to understand differential extraction is very important. Then we have the chromatography, very important. All right, then look at this, guys. Now our next topic is, our next method of purification is differential extraction. Differential extraction, very important, very interesting. This method is used to separate a given organic compound present in an aqueous solution by shaking with a suitable organic solvent. Now let's understand this. What is the meaning of differential extraction? So let's suppose you have an aqueous solution of your organic compound, guys. All right, you have an aqueous solution of your organic compound and you want to separate it from the water. You want to purify this. So what you will do, you will take a organic solvent. You will take a organic solvent in which the organic compound is more soluble than water. Let's understand this. The first thing you have is the organic compound, which is right now miscible in water. So you will add an organic solvent into it. Organic solvent into it. Okay, now, okay, you will take these two in a single beaker. Let's suppose in this thing. All right, guys. Now what you will do, you will make sure that the the solubility of this organic compound should be more in organic solvent that you have taken rather than in H2O. Now after having these two in a single beaker, you will start to shake it, guys. You will start to shake it like this. All right, you will start to shake it. Now when you shake this, there will be a disturbance, there will be a breaking up of bonds just because of the shaking, and somehow the organic compound, just because of this shaking will move towards the organic compound and will make new bonds with organic solvent and will take away the water molecules. And after 5 minutes or 6 minutes this shaking, you will have this scenario. Now let's look at this. This was the solvent layer before, because the density was different. So this was the solvent layer, this was the organic compound in aqueous form. By after this shaking, so you will have the aqueous layer separated completely, because after some time your H2O is going to be separated and you will have the organic compound along with this organic solvent. Okay, organic solvent. All right. Okay, and then finally you will have this scenario. Okay, organic compound, solvent layer. So this basic requirement of this organic solvent is that it should be immiscible with water, so that organic compound and water layers can be easily separated. All right, so this was differential extraction. All right, then the process can also be used to separate two organic liquids such as aniline and water. Understood, guys? Any doubt, anyone? Everything is okay? So in differential extraction, you have an organic compound, you have an aqueous solution of an organic compound, and you will add an organic solvent into it, in which the organic compound is more soluble rather than in water. You will shake the whole thing together, and just because of that shaking, the bonds will break up, and organic compound will get dissolved in the organic solvent rather than in water, just because the solubility of organic solvent with organic compound is higher. Clear? All right, then let's move to the next and the last technique of purification. Very important, very important. Let's understand chromatography. Guys, what do we mean by this chromatography? This is a modern method used for the separation of mixture of its components. All right, you will purify this compound and you will test the purity of the compound using chromatography. Now the first, this chromatography, where this chromatography comes from, this chroma means nothing. This chroma means nothing but, guys, color. So this method was first used to differentiate between the colors, to separate the colored substance found in plants. So that's why we call this chromatography, and this technique we can now use to separate our organic substance. But now let's understand how. Look at this, guys. So first of all, in chromatography, to understand the principle of chromatography, you have to understand the first thing. Okay, so chromatography works on the principle of adsorption. You know very well what is adsorption. Okay, now let's understand the process. Let's understand the principle. The technique of chromatography is based on the difference in the rate at which the components of a mixture move through a porous medium called stationary phase under the influence of some solvent or gas called moving phase. Now let's understand this principle using this diagram, guys. So in the very first case, you will have a setup like this, where you will have an adsorbent, which we are calling the the stationary phase. The stationary phase. All right then. Okay, there is a glass wool at the downside. All right, and you will add the mixture of your organic compound. Okay, or let's say you have the impurities along with this organic compound, or you can have two or more organic compounds which are miscible to each other, and you want to purify them. Even then you can use chromatography. Now this is adsorbent and this is your mixture. Now how we can say that our this mixture is is going to be separated. Now let's understand this. Okay, now this stationary phase is a solution which we are calling it as as an adsorbent. So it has very high tendency to absorb other substance with it. All right, guys. Now when it is going to be absorbed, it is it will absorb the components of the mixture. Now let's understand the degree of adsorption in both of them is different. Okay, it is going to be absorbed more. It is going to be absorbed more as compared to the impurity. In that manner, you will see the one which absorb more, which goes higher along with the or let me give you one very basic example. All right, let's understand this with the help of column chromatography. It is going to be very easy to understand this with the help of column chromatography. Now let's understand what is column chromatography. In this method, a suitable adsorbent like aluminium oxide, silica, magnesium oxide, and any other solvent, adsorbent you will take. Okay, you will take this adsorbent in a column, in a burette, like a long tube fitted with a stopcock near its bottom. Let's understand with the help of this diagram again. Now what will happen? A plug of this cotton or glass wood is placed at the bottom, the column to support the adsorbent. Here we have the glass wool which is going to support adsorbent. All right, this act as a stationary phase. The mixture to be separated is dissolved in a suitable solvent, and the solution is poured on the top of the column of the adsorbent. Because different components of a mixture has a different degree of adsorption, now this stationary phase will start to absorb the mixture components, and when they are getting adsorbed in this adsorbent, the one which is getting more adsorbed will travel the more. Let's suppose this is the C, which travels the more. So it is the reason why C travels the more is just because C is more, the degree of adsorption in case of C is very higher, just because it absorbs more now as compared to B or C. In this manner, just because of the difference in the degree of adsorption, you will see different bands of different things. Let's suppose you have three organic compounds. There is a mixture of three organic compounds. All right, but the degree of adsorption for all of them is different in this particular adsorbent. So by just after the adsorption, they will move the different distance. Just because of this, you will have three different bands of those three organic compounds, and then you will separate out all of them by opening this knob, and you will have the different. Okay, you will open it and you will first take this C out, then you will close it, you will take again the next beaker, then you will take this out, and then you will take this out. This is what we call as column chromatography, and this is one of the very important method to separate out the organic compound. Now let's understand the second method or the second case of organic compound, which we call as thin layer chromatography, guys. Thin layer chromatography. So first of all, in column chromatography, we have three organic compounds. We have three organic compounds miscible together, okay, and we separate out them with the help of the column chromatography. Now let's understand thin layer chromatography. What is there in thin layer chromatography? Now let's understand this. This method involves the separation of the substance of a mixture over a thin layer of an adsorbent coated over a plate. What will you do? Let's understand this. You will have a chroma plate which is made up of an adsorbent, all right. You will have a solvent in this beaker. You will have a solvent in this beaker, okay, and you have an organic compound in which there are a number of organic compounds miscible to each other. So let's suppose you have that organic compound. So you will take a limited amount of that organic compound and you will put a spot of that organic compound on this chromatographic plate. All right, guys, this spot is nothing but a mixture of different organic compounds. Now as soon as you will dip this chroma paper along with this spot of this organic mixture into the solvent, just because of the capillary nature, this solvent will starts to rise up. This solvent will starts to rise up inside the chroma paper, and just because the adsorption, the degree of adsorption in this particular adsorbent, this solvent of different organic compounds is different. Now let's suppose the degree of adsorption of the first organic compound is higher, so it will adsorb more and it will travel more. Let's suppose the color of this organic compound first is red, okay, or let's say is black, so it will adsorb more, so it will travel more with the solvent and will reach up to here. But the degree of adsorption of the other one is not as much as the first organic compound. It will just come along with the solvent up to here. So in this manner you will have two different organic compounds on this chroma plate, and this is what we call as thin layer chromatography, guys. Understood? Everything is okay? Now there is a very important term in this whole chromatography, and very important question, okay, from this topic can be the thing is retention factor, guys. What do we mean by retention factor? All right, now let's understand this retention factor. This retention factor is nothing but a ratio. And what's the ratio? Let's suppose you have this, the baseline, there was the spot at this point. Now the solvent will run from this chroma paper to the upwards, just because of the capillary nature of it. All right, so let's suppose you have the solvent here, okay. Now this solvent will pass into this chroma paper, let's say up to here. All right, but just because of the degree of adsorption, the organic compound only reaches up to here. This is the spot component, okay, organic compound. Now the distance that has traveled by the spot was x, the distance traveled by the solvent is y. So the ratio of these two is what we call as the retention factor, guys, is what we call as the retention factor. And this is how you use chromatography to separate out, to purify your organic substances. And that's it, guys. This was your whole method of purifications. Now let's move to the next topic, guys. Let's move to the next topic. Let's understand how do we analyze qualitatively of all the organic compounds. Now let's understand the first, detection of carbon and hydrogen, which we also call as copper oxide test. What we will do in this case, guys, we will have an organic compound, let's say CXHY. All right, this is an organic compound. Let's suppose we do have this organic compound CXHY. So we'll add copper oxide into it. Now from this organic compound, the carbon will react with the copper oxide, the dry copper oxide, and if we heat this whole thing, so we'll have CO2, because carbon will replace the copper and will make CO2 and copper. Now we want to detect if there is a carbon or not here. But if we are saying that if we add copper oxide into this organic compound, we don't know whether it is an organic compound or not. If it is, so the carbon from this organic compound will definitely going to reduce copper and will make carbon dioxide out of it. As you know, in the same manner, this hydrogen also will do the same and will make H2O. If this is an organic compound, there is a carbon and hydrogen into it. Now, if you know, this is the case and we want to test, we want to characterize this result, we know that if we pass carbon dioxide, you know, through your quick lime, you know, lime water will have, you know, lime water turns milky just because of the formation of calcium carbonate. And if this is the case, we can see that by passing it from lime water, if it turns milky, then there will be you know, detection of carbon, just because there is a carbon dioxide here. And if we, you know, during this whole process, when we have this water and you know, we have the test tube from which the carbon dioxide is coming and H2O is coming, will have a bulb with copper sulfate here. As soon as this copper sulfate get hydrated just because of the production of water here, this if there is water here, the copper sulfate will get converted into the hydrated form, and we know that hydrated copper sulfate has a blue color, which is a characteristics here. And if we get the blue color in this bulb just because there is a copper sulfate here in the bulb, we can identify that yes, we have this water here, and if there is water, there is a carbon dioxide here, we can identify that this organic compound contains carbon and hydrogen. So this was the detection of carbon and hydrogen, guys. Okay, first of all, very important, in most of the cases, you know, the reactions, you know, in these cases the reactions are not as much, you know, as that important, as you can tell how you will detect the two carbon dioxide and, you know, the water. That you need to know that we must have copper sulfate, we must have, you know, lime water, and this is how you can identify this. Next, guys, next, detection of nitrogen, guys. In detection of nitrogen, or I can say in detection of sulfur too, or in detection of halogens too, okay, we need one thing, which is lysine test. And what is this? Or lysine extract. In this extract, we are going to react our organic compound, the element from our organic compound, with sodium. If there is carbon and nitrogen in the organic compound, you know, there will be a sodium extract, which is NaCN. If we have sulfur in the organic compound, it is going to form Na2S. If we have halogen in the organic compound, we will have NaX, and then we'll do further detection of these compounds. But the important thing is we must have the lysine extract to detect nitrogen, sulfur, or halogens. Now let's understand what will happen in the case of nitrogen, guys. In case of nitrogen, we'll first add my organic compound with the sodium, which will give me the lysine extract or the sodium extract. Now using this NaCN, I'll treat this NaCN with the freshly prepared FeSO4. Just because of this, I'll have FeCN2, which I add further. You know, if I add further NaCN into it, I'll have this sodium hexacyanoferrate. All right then. Now, if I add FeCl3 into this sodium hexaferrate, I'll have a complex compound which has a characteristics color Prussian blue. And if I have this characteristics, I can tell that yes, we must have a nitrogen into, you know, in this extract, and that's because I'm having this characteristics color. So this is very important for the detection of nitrogen. So first case, you will make the lysine extract, the sodium extract. Then you will treat this sodium extract first with ferrous sulfate, you know, FeSO4 freshly prepared. Then you will treat the product with again NaCN, and then you will treat this sodium hexaferrate with FeCl3. Very important. Now let's next move to the next one, guys. Detection of sulfur. Detection of sulfur. Again, for the detection of sulfur, we require the lysine extract. So we'll have the sulfur from organic compound. From the organic compound, we'll add sodium into it, so that we'll have the sodium extract or the lysine extract Na2S. Now, if I treat this Na2S with lead acetate, I'll have a black color precipitate. A black color precipitate. If I get this black color precipitate, then I can tell yes, this is Na2S, which comes from the, you know, the formation of lysine extract from the organic, the sulfur from the organic compound and from the sodium. So this is the detection of sulfur. Very, very important reaction. You have to remember this, all right, for the detection of sulfur, my boys and girls. Now, let's move to the detection of halogen. Detection of halogen. Again, you will have to make lysine extract, sodium extract. So what you will do, you will have your halogen from the organic compound, okay, which is going to react with the sodium, guys. And as soon as this sodium will react with the organic compound, chlorine, bromine or iodine, it is going to make lysine extract for you. For example, it can be NaCl, it can be, NaI, all right, or it can be your NaBr. All right, guys. Okay, then now what will happen then? So in case of first one, NaCl, you have this NaCl, this chlorine is from the organic compound that you have taken, which you want to detect. So you will add all these three with AgNO3 silver nitrate. Just because of the displacement reaction, every time you will have a precipitate, PPT, guys. You will have a precipitate. Every time you will have a precipitate. If you look at this, okay, AgCl is a precipitate, which is a white color precipitate, guys. Again, AgBr is a precipitate, which is dull yellow, PPT, guys. And again, if you have NaI, if you react it with the silver nitrate, again, you will have a precipitate, which has a characteristics color, bright yellow, PPT. Yes or no, my boys and girls? So this was the detection of what? Halogens. Okay, so we have done for halogens, we have done for carbon and hydrogen, we have done for nitrogen. Now let's move to the next topic, which is the quantitative analysis of organic compounds, guys. Quantitative analysis. Now let me tell you one very important thing. The first topic which we have taken in this session was the purification. Complete theory, okay. You have to remember the examples, the principle of all these methods, all those methods. The first thing. The second thing was qualitative analysis. In the qualitative analysis, you have to remember the chemical reactions. But in the quantitative analysis, yes, you have some certain chemical reactions which are very similar to the qualitative analysis of all these, carbon, hydrogen. This was the same reaction which we consider in the qualitative analysis. But in this segment, you have to remember the formula to solve numericals, guys. If from this topic, the question will ask very, very important numericals from all this quantitative analysis. So always focus on the formula in this case. Now let's understand the estimation of carbon and hydrogen. So again, we have the carbon from the organic compound, guys. From the organic compound, we have the hydrogen from the organic compound. They will reduce your copper and they will make carbon dioxide, they will make H2O. Now if you look at this, you have a stoichiometric relationship between copper and carbon dioxide, between hydrogen and H2O. If you apply the basic stoichiometry in these two reactions, you can find the percentage of carbon by putting the molar mass of carbon divided by the molar mass of CO2 multiplied with mass of CO2 divided by mass of organic compound, because you want to find the percentage, so you will multiply it by 100. Now if you look at this, this is the given mass of carbon here in this equation, guys. In the first equation, you will divide the mass of given mass divided by the mass of organic compound, and then you will multiply this with 100. You will have the percentage of carbon. So this is the mass of carbon. This is the whole mass of carbon using the stoichiometry. I'm not getting into the stoichiometry because it will take a lot of time, and this is a one short session, very well. Similarly, if you want to find the you want to quantitative analysis of hydrogen, you will again have the percentage of hydrogen using the stoichiometry here, guys, and you will take the hydrogen and H2O has a relationship. So you will have the molar mass of hydrogen, which is 2, molar mass of your H2O 18 multiplied by mass of H2O given here divided by the mass of organic compound. You will multiply it by 100, and now you know this very well. This is the mass, the given mass of your hydrogen here divided by the mass of organic compound. You will have the percentage of carbon, percentage of hydrogen in this case, and this is how you can quantitatively analyze both of these carbon and hydrogen. So always remember these formulas, very, very important, very, very important. Now let's move to the next one, guys. Let's move to the next one. Estimation of nitrogen, guys. You want to estimate nitrogen. To estimate nitrogen, you have two methods. One is Dumas method and one is your Zeldal method. Okay. using these two methods, you can identify your nitrogen. Now let's look at the first method, which is Dumas method. In this Dumas method, you have the carbon from organic compound, you have hydrogen from organic compound, and you have nitrogen from the organic compound. All the starting two reactions are the same which we had in the estimation of carbon and hydrogen. So you will use the same formula for both these two. But in the next case, you have to set up a stoichiometric relationship between these two. All right, and here I can say that this is in gaseous state. So you have to apply the condition of STP here. When you apply, you can have the percentage of nitrogen here. So molar mass of nitrogen to be 28 divided by 22,400. Okay, done. And then the mass of nitrogen divided by nitrogen gas, and the mass of organic compound multiplied by 100. Okay, so there is a relationship of nitrogen atom with nitrogen gas. So using this stoichiometric relationship, you can find the percentage of nitrogen in the given organic compound using this formula. Okay, so this is nothing using the stoichiometry, but the mass of nitrogen in the organic compound divided by the mass of organic compound multiplied by 100. This is how you get the percentage of nitrogen using Dumas method, guys. Now the next one, Zeldal method. In Zeldal method, guys, you have some different reactions. In this case, you will first have your different elements in the organic compound, let's say carbon, hydrogen, sulfur, or nitrogen. Okay, so you will react this whole organic compound with the acid. Okay, so you will react this whole organic compound with H2SO4. This will make you CO2, H2O. You can detect all these with the same method like we did in the previous one. But in case of nitrogen, it will, by reacting it with H2SO4, it will make ammonium sulfate first. And when you react this ammonium sulfate with sodium hydroxide, it will make you ammonia. Now, in the final reaction, you will neutralize this ammonia using this acid, and to estimate your nitrogen, you will apply the stoichiometry in the final equation, guys. In the final equation. Now, in this final equation, if we apply the Zeldal method, if we apply the stoichiometry, the percentage of nitrogen is going to be 1.4 multiply molarity of acid you have taken, which is HCl here, multiply by basicity of this acid, multiply by the volume of this acid, divided by what? The mass of organic compound, guys. Mass of organic compound. This is how you can find the percentage of nitrogen using Zeldal method. Very, very important for your examination, for your NEET and for your JEE. So let's remember, make sure that you remember all these formulas. Next one, guys, next one. And in the next one, we will detect the halogen. We'll estimate halogens, guys. We'll estimate halogens. Now, for halogen, we will use Carius method. What will happen in Carius method? Now, let's look at this. You always have X halogen here. Okay, not halogen, I can say. You will have the lysine extract. Okay, let's say NaCl. Okay, you will have NaI. Okay, you will have NaBr. Okay, so all these when react with AgNO3 will make you AgX. So there will be a stoichiometric relationship between this halogen ion, okay, with AgX. Now, how will you find the percentage? Now let's look at this. Percentage of halogen is going to be, all right, then there will be a relationship between these two. All right, so first of all, mass of this X ion, okay, X is nothing but the halogen. It can be chlorine, iodine, or bromine, divided by the molar mass of AgX, multiply by the given mass of AgX, divided by the mass of organic compound, multiplied by 100. What does it mean? Let's understand this. If you have, let's say, for chlorine, what is the mass of chlorine? 35.5. Okay, in that lysine extract, divided by the mass of, now let's suppose this is for chlorine. So AgCl, you will calculate the mass of AgCl, 108 plus 35.5. okay, the mass of AgCX, which is given to you, the mass of organic compound, which is given to you. So you will have this from the question, and you will solve this, guys, and you will be able to detect or estimate the percentage of chlorine. Here in this case, as in the same manner, you will be able to find the percentage of bromine, the percentage of iodine in this case. Now, the next and the last estimation of sulfur, again using the Carius method, guys. All right, estimation of sulfur for using Carriers method. In Carriers method, what will happen? So you will have the sulfur from the organic compound, which will react, which will react with water and with nitric acid, and it will convert, we will get, will oxidize it to form H2SO4. Then further in the second case, we will have this H2SO4 and will react this H2SO4 with barium chloride to finally make barium sulfate, guys. Now, let's understand. We have a stoichiometric relationship between this sulfur from the first reaction to the barium sulfate, and using the stoichiometric relationship between these two, we'll have the percentage of sulfur, guys. We'll have the percentage of sulfur. So, molar mass of sulfur 32, molar mass of barium sulfate, because we need a relationship, stoichiometric relationship between sulfur and barium sulfate. So, you will calculate this, you will have 33. Okay, mass of BaSO4 given to you in the question divided by the mass of organic compound in which the sulfur is present multiplied by 100. This is how, guys, you calculate, you estimate the percentage of sulfur. Again, I'm telling you, in this whole session we have completed three things, guys: purification of organic compounds, we have completed the qualitative analysis, and then finally quantitative analysis. Guys, in purification you have to remember the examples, the principle of all the methods. That's it. In the qualitative method, you have to remember what is Lassagne extract, okay, what are the chemical reactions, okay, with which I'm going to react this extract. Those chemical reactions are very important. In the final quantitative analysis, you only have to remember these these formulas. Okay, if you remember these formulas, you can solve any question from this quantitative analysis of organic compound. I think you understand everything. Thank you so much. We'll meet again in the next session. Till then, guys, thank you. Bye. Bye, guys.